When investors think about the hardware powering modern artificial intelligence, they usually look at a single company. NVIDIA's graphics processing units power such a massive share of the AI training market that the company's valuation recently pushed past $4 trillion. But while NVIDIA dominated the public headlines, Alphabet spent the last decade quietly rebuilding its own infrastructure. In the background, they have been designing custom tensor processing units, specifically to run Google's internal workloads. To understand why they took this path, you have to look back to 2015. Google's engineering teams were looking at the sudden rise of Android voice search, and their internal projections triggered an immediate panic. They calculated that if every Android user utilized voice search for just 3 minutes a day, Google's global computational demands would immediately double. Solving this through traditional hardware was impossible. Purchasing enough standard servers to meet that demand exceeded their planned capital budgets, and their existing data centers lacked the physical space and power to sustain that many machines. They were facing a hard physical limit. Surviving this bottleneck required Google to abandon standard microchip design and build something entirely new. At the time, general-purpose CPUs and GPUs were designed for versatility. They functioned like computational Swiss Army knives, built to handle everything from video game rendering to complex spreadsheet calculations. To maintain that versatility, these chips use power-hungry features like out-of-order execution. Out-of-order execution is a process where a processor predicts and runs instructions ahead of time to speed up complex tasks. But for the repetitive, sequential math of neural networks, those features are just dead weight burning electricity. Google issued a 15-month engineering mandate, deliver a 10-fold leap in AI performance. That timeline forced them to develop an ASIC. An ASIC, or Application-Specific Integrated Circuit, is a custom chip hardwired to perform exactly one task with extreme efficiency. This is the physical printed circuit board for the result, the Tensor Processing Unit, or TPU version 1. Engineers stripped away the general compute logic, leaving only the specialized components needed for AI. By discarding versatility, Google unlocked levels of data center efficiency that allowed their services to scale without doubling their power bill. This quietly launched a new silicon arms race inside their own server racks. Stripping away that general-purpose logic freed up a massive amount of physical space on the silicon die, which Google used to optimize how the chip processed data. This diagram shows the TPU's architecture. The yellow matrix multiply unit dominates, housing a massive systolic array that rhythmically pumps data like a heart. Notice the data flowing directly from the blue unified buffer into the matrix, achieving massively higher throughput by eliminating memory stalls. This chart shows the energy impact of that design. Focusing on the tall green bars on the right side, the TPU provided up to 80 times more operations for every watt of electricity consumed compared to existing CPUs and GPUs. While the first version proved the concept for running AI, Google now faced a new problem. They needed hardware capable of training the massive models that were starting to define the industry. As the scale of neural networks exploded, Google iterated through versions 2, 3, and 4, shifting their engineering focus toward the massive computational demands of training. Training generates intense heat and requires specific mathematical precision. Google introduced liquid cooling to manage the thermal load and adopted bfloat16 for their calculations. bfloat16 is a specialized 16-bit numeric format that allows for faster math while keeping the wide dynamic range needed for deep learning. By version 4, Google began using optical circuit switches to network thousands of chips together. They used mirrors and lasers to route data directly between server racks, creating massive, unified supercomputing pods. The real-world test for this scaled architecture was Gemini 3, Google's flagship trillion-parameter AI model. Internal documentation revealed that every phase of Gemini 3's training ran entirely on Google's own TPU pods. They developed one of the world's most advanced models without relying on a single NVIDIA GPU. By training its most complex model on its own hardware, Google proved that a vertically integrated stack could credibly compete with the GPU-based clusters used by the rest of the industry. Google is now deploying its 7th-generation TPU, named Ironwood. It is engineered specifically for the age of inference, optimizing for the workloads of serving millions of AI queries back to users quickly and cheaply. An Ironwood pod can deliver 42.5 exaflops of compute power. An exaflop is a unit of performance equal to 1 quintillion floating point operations per second. This scale allows Google to process massive volumes of AI requests with significantly lower latency than general-purpose hardware. Other developers are noticing. The AI startup Anthropic detailed plans to use as many as 1 million Ironwood chips to power their Claude language model. This external adoption reveals the economic strategy behind the program. While NVIDIA generates revenue by selling individual chips to many different vendors, Google controls a full-stack ecosystem. Google owns and optimizes every layer: the custom silicon, the networking infrastructure, the physical data centers, and the software frameworks.
Because they control the entire stack, they can tune their data centers around their own silicon, allowing Alphabet to capture higher margins on every AI dollar spent in their cloud. The journey from a search engine crisis to the Ironwood pods proves that the AI hardware market is becoming a heterogeneous landscape. The future will be defined by highly specialized, vertically integrated ecosystems designed from the silicon up.